Hi, my name is Gerhard Kut. I'm presenting for Jack. This is mostly Jack's work. Jack suffered a stroke about 3 years ago, and so he's going to answer all your questions, and I'm going to do the presentation. So thanks very much for coming. So we're going to start off with, we have a little toggle for everybody here. It contains a lot of the information that we're presenting, but this topic is so big that we decide to give some things out to be a little bit more accurate. So these are some of the files on it, and there's quite a lot of information there. So we're going to focus on 15 good reasons why trimarans are better, and that's what the talk is going to be about today. So we're going to try to go through this as quickly as possible. If you have any questions, please feel free to ask. Okay, so the introduction is Jack here in 2000. He bought Prout to build expensive toys for rich people. And he moved from catamarans to trimarans. Prout was essentially a catamaran builder. One of them was developed together with Professor Hopper here with the foil system. And that's what really interested Jack. So he bought the company and started producing catamarans. He soon went to trimarans because it was this area that piqued his interest. In order for the science of trimarans to benefit us, we need to bring the theories to specific projects like workboats and ferries, and that's exactly what Jack's been doing. So Cheeta Trimaran takes up the responsibility of developing low-cost production methods using very high-tech materials. We're talking about carbon Kevlar, titanium composite materials with epoxy, and to make it affordable so that it makes sense to end users. So right now we're working with some countries who require a fleet of boats. So we will develop the molds, the tooling, we'll build the prototypes, customize the design, and bring it to the country so that it can be built there. So we bring all the materials there as well. And that's the idea of how we're going to bring very high-tech, relatively expensive materials at a very efficient production methodology to bring the cost down for producing boats. So Jack's been a busy man. He's produced lots of different hulls. He's built 11 prototypes, which the world has not seen, except for one or two of them. And so he's been messing around with a lot of different boats. So he's been very busy. The boat that we're featuring mostly is this green boat called the Sidewinder. It's 01. It's currently in Hong Kong. And my experience with it was I met Jack and he says, "Hey, come drive my boat." So I thought, well, this boat looks interesting, but I don't think it's going to do very much. Now, I come from a hydrofoil background. My boat at 4,000 RPM with twin outboard engines does 28 to 30 knots. I get on this boat and we're cruising at 36 knots at 4,000 RPM. So my jaw dropped and I said, damn, I'm in trouble. My boats can't go that fast anymore. This one does. So let's go into why now trimarans are better. So the first one is you have a trimaran with 3 equal hulls, and the 3 equal beam hulls has 48% drag of a normal monohull. It's the form drag is 80% of an equivalent wet beam catamaran hull. So trimarans are 50% more efficient than monohulls and 21% more efficient than catamarans. Okay, propulsion. The reason I like trimarans is with cats, you have to start with 2 engines. You can go with 1 engine, but it's not that great. Trimarans, you can go 1, 2, or 3 engines. So with less form drag, you require less engine power. You have less fuel because it's a lighter boat, and equivalent power yields higher speed. Now, we're specifically talking about trimarans with very exotic materials, so it's super light. Okay, so trimarans work much better when they're really light. Aerodynamic advantage. This is an area of Jack's expertise. We bring in aerodynamic lift advantage. A delta wing shaped design is a lifting body. The ground effect produces a glide ratio of up to 4.5, whereas a monohull is less than 1. So Air entrapment in the hull tunnels provides some lift, but really it's the surface of the boat on the side here, along the side here, which actually produces more lift than the air entrapment underneath. And that's where the design comes in. So we're going to look at structural requirements. We have the increased rigidity of 6 sidewalls, and so it becomes a box or an I-beam rigidity, which reduces structural requirements. We have a monocoque hull, like all cars are built today, and that then increases the interior volume while still retaining strength. Then the use of very, very high strength, state-of-the-art lightweight materials such as carbon, Kevlar, titanium reduces the structural requirements further. So reduced structural elements reduces overall weight of the boat, so we can go a bit faster. So we have a better ride. Jack discovered that in cats, there's a corkscrew motion that occurs, and that's uncomfortable. It reduces seasickness. So by having the third hull, it reduces that. The narrower hulls can absorb incoming waves more effectively. By adding the pads, we have 6 pads, and that basically gives us a faster ride, less resistance. A wider hull, sorry? Oh, sorry, the pads are what we call the things that, there's a pad over here when you're going along, there's a pad here, and there's a pad there, and the rest is all air. So you have a, oh, you don't? Okay. Okay. Well, we'll ask, can we answer the questions a bit later? Yeah. Yeah, these are the steps. Okay. I'm not a fan of steps. Jack is a fan of steps. Anyway, so it's the steps, yes. Yeah. The wider beam gives lateral support, so it's a more stable ride, and the aerodynamic lift at higher speeds also stabilizes the vessel. And we also find reduced porpoising. So the next one is a larger usable area. We have wide beams, so it allows for much more variations in deck design. Improved controllability, we have 6 sides, so directional stability is superior. We have less tail sliding, and turns are smooth and controlled. So this shows the bottom of the boat. It's a very wide boat. High sea state operation. Okay, so we looked at different designs of hulls, comparing catamarans and trimarans. Skinny triple hulls obviously is a softer ride. It slices through waves, and so you have a softer ride. Trimarans can operate more smoothly in high seas, and we went from from Hong Kong to Macau, sea state 3, and we were averaging 36 knots. So that was that surprised me because I didn't think that the boat could do that. So I was very surprised. Wave dissipation. This is reduced vertical acceleration. Wave dissipation occurs in tunnel spaces between hulls drastically. So basically, you have a high tunnel, and the waves can move up and move up into the tunnel quite high, and that reduces g-forces. Vertical accelerations for closely spaced fat hulls of catamarans, you have a harder ride, are reduced by about 20%, and thin-walled trimarans goes up to about 40%. A deep V here also reduces slamming. So unparalleled height speed safety. The delta-shaped configuration of the hull is very much like a delta wing aircraft. We call this mushed forward motion. At high angle of attack, a delta wing aircraft doesn't stall, it mushes. That's a aircraft technical term. So like the space shuttle, it was designed as a delta wing aircraft because it doesn't stall, it mushes. The center of lift of a delta is very close to the center of gravity of a hull. Same with the trimaran. In catamarans, the center of lift is far ahead of the center of gravity, which sometimes means at very high speed, a catamaran will flip over the longitudinal axis. Okay. We have triple hull safety. This is on buoyancy. We have 4 to 6 watertight compartments, so the boat is virtually unsinkable. Composite reinforced hulls and center hull fuel tanks. We can render the fuel tank bulletproof to a certain degree. Environmentally friendly. We have the trimarans riding at a very high. They ride very high, so basically the wakes are a bit lower. The wakes are dissipated through the outside hull as well to a certain degree. And with the high efficiency, we also burn less fuel, and there are lower emissions. So here's just an idea of, the boat riding. So the top speed of that boat is 52 knots, cruising at 36. I think when it was brand new, without anything on the bottom, it was close to 40 knots cruising speed. So Jack has found 22 variables that he can play around with on the boat. I don't know what those 22 variables are. You'll have to ask him. So there's many more ways to optimize the design of the hull. So there's a lot of things that you can play with. Multiple deck choices means that you can customize a boat exactly for whatever mission you want to design the boat for. It is perhaps one of the best options for an unmanned surface vehicle. At very high speeds, the delta-shaped trimaran is the most stable platform. When I was riding it, what I found was at 50 knots, the boat rides softer than at 40 knots. And that's because the aerodynamic effect takes precedent. So when you take off a wave, it actually becomes very, very soft. And that kind of blew me away because I didn't expect that. The trim angle variations are reduced due to lift and LCG positions being very close. So the boat rises as an entire unit. You don't have the bow going up a lot. So it's a very stable platform. That's why we think the trimaran is therefore the best candidate for a USV. The wow factor, we think that it's a really attractive looking boat. Some people say that catamarans are not that attractive. A monohull is a very attractive boat, and likewise I think a trimaran is as well. So that's the boat that's in Hong Kong. And thank you very much. If there are any questions, Jack will help answer some of them. Thank you. Can I take questions? Yes. Okay, so the question is, when a boat has a very high angle of attack over a wave, how do you handle the boat? Okay, all right. So in rough conditions, I have not yet encountered the angle of attack going really, really high. The main reason is when we hit a wave, the boat still slices through it. The bow is fairly narrow, and what I found is that the entire boat lifts and then the entire boat comes down. So we don't get that porpoising action. So I haven't encountered it yet. Jack, do you have an answer to that?
Basically, if you look at...
Use the mic. Yeah.
Basically, if you look at jet fighters 20 years ago, they are just a typical aircraft. But you look at all the modern jet fighters, they're all deltas. Like, for example, F-16, F-18, we call it you walk the field. So you basically can fly the airplane like this around the airport, and they don't stall. You can't do it with the traditional aircraft. So basically, when it's delta, you don't have a sudden departure from a stall. Just like a high-speed boat, they have a sudden departure, and then it's over. But a delta boat will not do that. You would start to feel mushy around, and then you just hang on there, and the thing will just come down because the boat is very, very light. So it's actually, you could feel a little bit airborne. Even at a very low speed, you could see the effect of the air acting on the top of the boat. I think if you go to the big file we have, there's a video
Okay.
that show the boat can go.
Yes, it is on the. It's on the.
Yeah, it's all in here. Everybody can have one.
Yeah.
Yeah.
Okay. Any other questions? Yes, sir.
The last boat we infused, I call it 03. I have a titanium bottom on the boat. So what I did is I take grade 5 surgical titanium and I found a way to infuse it into composite. In other words, these boats, you could infuse the whole hull in about 40 minutes. Within that 40 minutes, I can also have the titanium, the cover, the bulletproof proofing, everything all in one shot. The hull is built in one setting, 40 minutes. The deck, same thing. So there's only one joint on the boat, and that's the top and the bottom joint.
So the titanium is usually on the hull bottom.
Yeah. Why do we need titanium? Simple. Titanium have 30% elasticity. So let's say you hit a rock, right? So the carbon part of the hull would fracture, absorb a lot of energy. The cover part of the hull would hold it together still, but deform, because the cover don't have a lot of memory. The foam we use in the boat is a Gould M foam. They also have 30% memories, but elasticity as well. The titanium in the hull itself would change shape elastically and then bounce back the boat into the original shape and just keep going.
Any other questions? We're around for the next couple of days, so you can please feel free to meet with us. Take the little toggle. There's a lot more information on that. We have a lot of information on titanium as well. So if there are no other questions, thank you very much. Thank you.